Hi, welcome to the next of our series of mini lectures as we start a new project. The project this time is going to be building a spectrophotometer, which is a device to measure the intensity of light and to some extent the color of light. And as we go through this, we're going to combine both what we're learning about optics as well as some of our knowledge of electrical engineering and electronics. This is a overall diagram of the source. Electronics provides power to a light source. So we're talking about electricity, and I'll use the symbol for an electron E there. The light source puts out photons, h nu, which go through our optical system and go to the detector. And the detector we'll be learning about later converts photons back into electrons, which go, and then we process those with electronics. We can sort of divide this up into optical components, or things that optics have something to do with, and also things electronics have something to do with. And you'll notice there's some overlap between optics and electronics, which is why we're doing this particular project. Another way to look at the system is right here, where we look at it linearly. That power goes to a light source. The light source filtered, it goes through a sample, it's filtered again, is detected, and goes to electronics. And again, what we're talking about is electrons here, and photons, h nu, here, 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 here. And what we're going to be studying today is this idea of a photon, h nu. So why do I write a photon h nu, for example, and what is a photon? So let's do a quick review of that. Remember that we have three ways we can describe lights in this class. The first that we spent the first half of the course studying about is that individual particles of light move in straight lines, and we call these ray, and this is the domain of geometrical optics. What we're not going to study in this class is how light behaves as a wave, although we hint at it occasionally, and it's valid in 99% of the cases you're going to deal with. What we're going to do now is we're going to look at light as a quantum mechanical particle. And don't let this frighten you. Quantum mechanics just means that things have both wave and particle-like properties, and we'll study a little bit of quantum mechanics later. And if you do the full theory on this, this is the most complete explanation of light, but it's also the most complex, although we're going to simplify it quite a bit. So what I'd like to look at now is a picture from Wikipedia that looks at the electromagnetic spectrum. And you'll notice that light, the part of the electromagnetic spectrum we're dealing with, is right here. Its frequency is on the order of 10 to the 14th to 10 to the 15th hertz. We're talking about wavelengths on the order of 10 to the minus 6 or 10 to the minus 7 meters, or 100 to 1,000 nanometers. Things on the orders of protozoans and molecules are the types of things we're going to be talking about. And we'll ignore this graph underneath for the time being until we get to thermal sources of emission. But recognize that of the full electromagnetic spectrum, the visible light region that we're going to be working with is a fairly narrow part of it. So here are some equations that you need to have memorized or be able to really get at your fingertips if you want to be able to deal with photons. So let's go through each of these. First of all, the frequency and the wavelength of light, both given in MKS units, are related to the speed of light c. And remember, c is equal to 3 times 10 to the 8th meters per second. And so we can convert easily between wavelength and frequency. The energy of a photon is equal to h times nu, where nu is Planck's constant, or plugging our top formula in, the energy of a photon is hc over lambda. And remember, we can represent Planck's constant either in joules, the MKS units of energy, or electron volts, which is kind of nice because, as we see in this picture right here, in the visible region of the spectrum, there's that tiny little arrow symbol. Frequencies around 300 terahertz, wavelengths between 1 micron and 100 nanometers. In electron volts, we're talking single units, something like 1 to 10 electron volts. So we can work in very nice units of single digits if we use electron volts, but I personally prefer to work in joules. So again, the energy of a photon, how much energy a single photon contains, is Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. If you want to convert between joules and electron volts, you just need to recognize that the charge of the electron comes in here, and the energy in joules divided by the charge of an electron gives you the energy in electron volts. And so that's a fairly easy conversion to do. Another formula that we'll use later, but is important to throw out now, is the formula relating intensity, I, so there's intensity right there, and electric field, E. And that's related through the permittivity and permeability of free space you studied in your fields class. And you'll notice that intensity scales as the magnitude of the electric field squared. So intensity, since it's proportional to a magnitude, contains no phase information. It's power only, and it goes as the square of the electric field. The intensity in the photon picture of light is the photons per second per unit area. And we recognize anything in per second per unit area as a flux. And so an intensity is a energetic flux of photons. Power, which I tend to use interchangeably with intensity, although it's not, is the intensity multiplied by the area. And so it's the photons or energy per second. So power is given in terms of energy per second, or photons per second times the energy of the photons. And of course, the intensity is given by the power divided by the area, or intensity times the area equal power, as is shown in these lower slides here. And we'll show how we use that. I'm going to give a couple examples because I'm throwing these formulas at you pretty fast. And let me acknowledge that I took these images directly off of Wikipedia. So again, important things to recognize are how to go between wavelength and frequency, and that's related by the speed of light, knowing how to calculate the energy of a photon, knowing how to convert between joules and electron volts using the charge of an electron, E, which is 1.6 times 10 to the minus 19 coulombs, knowing the conversion between intensity and electric field, and knowing that power is equal to intensity times area, or intensity is equal to power divided by area, are very important things to memorize.